Okay, this is section 1.4, differentiation, and using limits of difference quotients. Differentiation just means that we're going to be able to take a derivative. So we're actually going to introduce the concept here of the derivative. So we're going to be able to find derivatives and values of derivatives, and we're going to be able to find equations of tangent lines, which is actually an essential part to be able to find derivatives. So some of the vocabulary we're going to talk about are tangent lines, instantaneous rates of change, which we did mention in the previous section, the derivative, and then the word differentiable, which again just means that you can actually take the derivative, that there's a way to find the derivative at a specific place. Okay, this is going to be much more concept based. Yes, we're going to be doing some problems and there will be some algebra, but there is definitely very concept based. So this is a really important lesson. In the previous section, we discussed average rates of change, which was the slope of the secant line. So basically, it was the average slope between 2 points, very much like you see over here in the right. If I wanted to find the slope between that point and that point, you can see that the secant line was drawn in there. As long as we know what the 2 points are, we can find that slope. And in general, what it was this difference quotient right there. That was the slope of the secant line. Well, the idea is now what if I wanted to find the point, or excuse me, what if I wanted to find the slope at just one of those points? I just want to find the slope right there. Well, in order to do that, in order to find the slope, you actually need 2 points. Okay, you have to be able to do a y2 minus y1 over x2 minus x1. Well, what if we decided to take and move the other point, the one that looks like it's about at 2 or whatever, and move it closer? Let's move it to there. Well, then my secant line looks something like this. Well, that's not really the slope that I'm looking for because the slope of that line needs to be the tangent line, or needs to be outside. So then what if I decided to move the point closer? Well, now mine is getting, that's actually looks like that's right along the curve. It's not quite, but it's just a little bit inside. Now my pen obviously makes it look like that it's, pretty much right along the curve, but it's not. It's actually on the inside. So the whole concept here is, what if we keep taking points which get closer and closer and closer to this one? And then if I take a point which is right here, that's now really close. So that's getting really close to the slope exactly at that point. The concept is this. If I can find the slope of the line which is tangent to the curve, meaning it's only going to hit the curve at one specific point, like the graph over here on the left, it's only going to, that you see that tangent line only hits the curve at that one outside point. If I can find out what the slope of that tangent line is, I have then also found the slope of the curve at that one particular point. Well, like what we did up here, what we were doing is we were taking and we were moving our secants much closer to the green. So we went from the orange to the red to the blue to the purple, and the process there is we're moving these things closer and closer and closer to the green. Or in other words, we're taking a limit. We're taking the limit of the secant slopes as that difference between the 2 points gets really small, and that difference between the 2 points is h. That was the difference between the two x values. So if we let that h value approach 0 and take the limit of our secant slope, we are then going to find the tangent slope, which is in turn, going to be the instantaneous rate of change. So let's go ahead and see if we can at least recognize what tangent lines are. Hopefully you can take a look at this graph and you can figure out which ones are tangent lines. Tangent lines are going to hit the curve at one point, and all of these hit the curve at one point. But they also kind of have to follow the direction of the curve. As you can see, L1 kind of like cuts through it. It's almost perpendicular to the curve. L3 looks like it is perpendicular to the curve. But T1, 2, 3, 4, and 5, all of those are tangents as they kind of skim the outside of the curve, but they're going in the same general direction as the curve. So it can't kind of cut through, it's got to go on the outside of the curve, if that makes sense. Hopefully it does by looking at it. And again, the next paragraph just says exactly what I said. We're going to let x to x plus h, that difference, which is just h, approach 0. So we're going to shrink that. We're going to take the limit as h approaches 0 of our secant. That will be our tangent slope, or the slope at one instantaneous spot. So let's go ahead and look at the next page. So the definition of the slope of the tangent line, you'll notice, is almost identical to the secant line. Once again, this part right here, if I just box this, that was the secant slope. Well, the only difference is now I am taking the limit of that secant slope and letting h, or the difference between the 2 points, approach 0. That becomes the slope of the tangent line, which we just call m, because it's the actual slope of the curve. It's the instantaneous slope, or instantaneous rate of change. And because this happens so often in calculus, we've given it a special name. Instead of always calling it the slope of the tangent line to f, we've just called it the derivative. So now we know how to find the derivative. And the notation for derivative, or one of the many notations for the derivative, is this, this symbol right here. We will learn other ones, but it's read f prime of x. The little apostrophe symbol is read as a prime symbol in calculus. So it looks like an apostrophe, but it's read as prime. So we're going to call this f prime of x. And f prime of x is exactly what we have written above. It is the limit as h approaches 0 of the difference quotient, f of x plus h minus f of x over h. So ultimately, when we find these derivatives, we're going to do what we did before. We're going to find the difference quotient, but then we're going to take the limit as h approaches 0. So again, step 1, write the difference quotient. Step 2, simplify the difference quotient, because you do need to simplify it so that you can get rid of that h in the denominator, which we talked about in the last section. And then we'll find the limit at the end of the difference quotient as h approaches 0. So let's go ahead and do that for example 1. So we have actually kind of already done some of this work before, but we're still going to go back through it again. So in order to find the difference quotient, we need f of x plus h. And f of x plus h, once again, is plugging x plus h in for the x's. So that's going to be x plus h squared. We are going to need to expand that. If we FOIL that out, which we have done before, x squared plus 2xh plus h squared. So now we're ready to set up the difference quotient. So the difference quotient is f of x plus h, which we just found, x squared plus 2xh plus h squared, minus f of x, which is the original function given to us, x squared, all over h. But if we want to find the derivative, we need to take the limit of that. So we're going to take the limit as h approaches 0, and all of this is the derivative f prime of x. Okay, so that's just all notation there, and notation is important, so make sure you're writing this in the correct notation. So let's go ahead and, again, we have to simplify the difference quotient first before we can take the limit. So because of that, we keep writing the word limit until we can actually evaluate the limit. So remember what I said is anything without an h in the numerator has to algebraically go away. The x squared and the minus x squared do go away. Both of the middle terms on the top have h in it, so we're okay right there. So we're going to have 2xh plus h squared over h. Still have the limit. Okay, we're going to take the limit as h approaches 0, because I still can't plug in 0 yet for h, because I'm still going to get a 0 in the denominator, which is not going to work. So we have to divide the h out of every term, and when we do that, we get 2x plus h, technically over 1. We don't need to write the over 1. Now we're in a position where we can actually evaluate the limit. I can plug 0 in for h now, and we're left with 2x. That is f prime of x. Now what it wants us to do is it wants us to actually evaluate f prime at a couple of different values. It wants us to do f prime of -1. Well, that's literally just plugging -1 into there for x. So we're going to get 2 times -1, which is just -2. And it also wants us to do f prime of 2, which is 2 times 2, or 4. And what does that mean? What it means is the slope of whatever this curve looks like, and this is just your standard parabola, the slope of that curve when x is -1 is -2. So it's coming down. The slope at when x is +2 is +4, so it's going up. That's what that means. All right, this next example is going to take a little bit more time because the function itself is a little bit more challenging to deal with, just like before, and we have done this one before. So if you've already done it and you don't feel like writing it all out again, that's fine. I'm going to still go through it. We need f of x plus h, which is 1 over x plus h. So now we have enough to go ahead and write the difference quotient, which is 1 over x plus h minus 1 over x all over h. We need to take the limit as h approaches 0. And that right there is going to be f prime of x. We'll write that notation in at the end. So remember on this one, we had to multiply the top and the bottom by the common denominator of x plus h. So then we're going to get the limit as h approaches 0. Multiplying the x times x plus h times each one of the numerators is going to give me x minus parentheses x plus h all over h times x plus h. Still cannot evaluate the limit because I've got to get rid of that h in the denominator. In order to do that, I can simplify the numerator. The x minus x is going to go away. Don't forget the minus gets distributed to the h as well on top. So you're going to have minus h over h x plus h. The h's now can divide away, and that's what we needed to be able to do. So then I've got to write this one more time. Limit as h approaches 0. Now I have -1 over x plus h. As h approaches 0, I can plug 0 in for h now. What that leaves me with is -1 over x times x plus 0. But x plus 0 is just x, so it's really just -1 over x squared. That is f prime of x. And then it says we want to find f prime of 2. That's the easy part. Once we get the derivative, the easy part is evaluating it at a number. We're just going to plug the number in. So f prime of 2 is -1 over 2 squared, which is -1/4. Okay, that's f prime of 2. Now part C says it wants us to find the equation of the tangent line to the curve at x equals 2. Well, if you're going to write the equation of a line, and we haven't done this yet, if you're going to write the equation of the line, you really need 3 things. You need the slope, which we just found, and you need an x and a y value. Because we're going to use the what's called point slope form of a line. Whoops, sorry about that. We're going to use point slope form. At least that's how it's going to start. Point slope form is y minus y1 equals m times x minus x1, where y1 and x1, where y1 and x1 are points, actual numbers that we're going to plug in, and so is the slope. We just found the slope. We know x1 is 2, that was given to us. So the only thing we have to do is actually have to find y1. Well, we can go back to the original function to find y, because, sorry about that, because, geez, y is going to be f of 2. Well, that's just going to be plugging 2 into the original function, so that's going to be 1/2. So there's our y value. So we have x, we have y, and we have slope. So let's plug those things into point slope form. So we're going to get, oh, jeepers, y minus y1, which we just found to be 1/2, equals the slope, which we just found right above, which is -1/4, x minus 2. That is point slope form of a line, and that is perfectly acceptable. If you had to put that into y-intercept form, the general idea is just add the 1/2 over. You don't really have to combine everything inside the parentheses, but if I wanted to write it in y-intercept form, I could just do y equals -1/4 x minus 2, and then add the 1/2 over. If you really wanted to put it into y-intercept form, you would distribute the -1/4 throughout, and then you would combine the 1/2 and whatever you get for your fraction. So that would be it. But the point slope form, this is probably the most easy way to write the equation of a line, especially in calculus. Okay, example number 3. Suppose f of x now is square root of 2x plus 1. What's the slope of the tangent line to f when x equals 4? So we're trying to find the slope of the tangent line when x equals 4. What that really is saying, we want to find f prime of 4. Well, in order to find f prime of 4, we need to find f prime of x first, so that we can plug the 4 in. So in order to find f prime of x, we do the difference quotient. So what we need is f of x plus h. And again, that's plugging x plus h into every x. So this is going to be a little bit more tricky. It's going to be 2 times x plus h plus 1, all under the square root. All right, so the difference quotient, f of x plus h, which we just found, 2 times x plus h plus 1, all under the square root. And then it's going to be minus the original function, which is square root of 2x plus 1, all over h. And then don't forget, you're taking the limit of that as h approaches 0, and that's going to be our derivative. So in order to do this one, you got the 2 square roots on the top. We're going to use the conjugate method, which is multiplying by the same exact square roots on the top, but with a different sign in the middle, so it'll be a plus, and do the same thing on the bottom. So we're going to get the square root of 2 x plus h plus 1, and then plus square root of 2x plus 1, and do exactly the same thing on the bottom. It's a little tedious to write this out, but it's not horrible. And then remember, when you multiply the tops, you're foiling it. So you're going to multiply the first times the first. And because the outside and inside are going to go away because it's conjugates, you're just going to multiply the last times the last. So let's go ahead and write our limit. Multiplying the first times the first is just going to give me what's underneath. So it'll be 2 x plus h plus 1 minus multiplying the outsides and insides, again, go away. So last times last is going to give me the same square root. So it's going to end up with 2x plus 1. Keep that in parentheses so we don't forget to distribute. And then don't distribute the denominator. It'll just be easier to simplify. All right, let's see what we can do with this thing. We do have to simplify the top. So it looks like I'm going to have to distribute this 2 into here. So we're going to get a 2x plus 2h plus 1, and then distribute the minus sign in the second parenthesis. You get minus 2x minus 1. over the whole denominator. Again, it just gets a little tedious to write all this out. So again, it's not horrible, it just takes a little bit of time. All right, let's see what's going to happen on the top. Let's simplify it. The two x's are going to go away. The 1 and the minus 1 are going to go away. That's really nice. That's going to leave us just with a 2h on top. So we're going to have the limit as h approaches 0 of 2h over h times, again, the entire parentheses. And then it looks like my h's are going to go away, which means now, after all that, I have to write it one more time. But then I'm going to be able to evaluate pretty soon here. So now we're just going to be left with this square root plus the other square root in the bottom. Now, if I plug in 0 for h, let's see, now we can actually evaluate the limit. If I plug 0 in for h, we're still going to get 2 on top. Plugging a 0 in for h on the bottom is going to give me a square root of 2x plus 1. And it's going to give me a square root of 2x. And it wants us to evaluate, because what we just found there, this is f prime of x. It wants us to evaluate that at 4. And something's not right. Oh, I wonder if any of you guys caught my mistake. I see what happened. I can't read my own writing, apparently. Up here, for whatever reason, I started changing the second square root in the denominator to an h. It should actually just be, here, let me see if I can erase this. It should actually be 2x plus 1. I knew something wasn't right there. That should be a 2x plus 1. This one right here should also be a 2x plus 1. So hopefully you caught that. If not, it's not that difficult to change. Just erase that real quick. There we go. And that makes that a 2x plus 1. Okay, perfect. So now if we were to plug in 4, we get 2 over. Plugging a 4 into the first square root is going to give me 2 times 4, which is 8, plus 1 more is 9. So we're going to get the square root of 9, which is 3. Plus, we're going to get another 3. So what we get is 2 over 6, which reduces to 1/3. And there you have f prime of 4, or the slope of the tangent to f at x equals 4. Okay, that's plenty enough for this section. You should have enough to do your homework, and we'll come back and we'll do the next section in a bit.